All right, let's talk in some detail about function inverses. So we've kind of dealt with this along the way. Anytime we made an arrow diagram and had to make an arrow that went back the other direction, we've been using this word inverse to describe what goes on that opposite directional arrow. Most of that for us has had to do with the transformations. But it certainly is true sometimes for functions as well. There's not a space to fill in something necessarily on notation on your notes. I've kind of put it in there for you already, but it's an important enough thing that I've got to, say something about it here. So when we want to talk about, if we have a function that we call f, if we want to talk about its inverse, the notation we use is this. That is read f inverse of x, and so it's a superscripted -1. When we're talking about inverses, it will never be anything except for a -1. And we need to separate that from the concept of x to the -1, which we know means 1 over x, and doesn't necessarily mean inverse. Okay? In some instances, it's kind of related to that, but we need to separate those ideas, and it should be clear from the context of the problem that when the -1 is attached to the name of a function, it means inverse. When it's attached to a variable or an expression, it means flip this thing over. Okay, so it's an intersection, unfortunate intersection of notations there. Now, getting down to business here. When we're talking about inverses, the idea is we're trying to reverse the process, and so everything switches. The x's become y's. The y's become x's. Input becomes output. The vertical becomes horizontal. Even when we're talking about asymptotes, vertical asymptotes become horizontal asymptotes when we go into an inverse. Okay, domain becomes range because domain was about inputs and range is about outputs. Outputs become inputs. Horizontal becomes vertical. All of these things switch, and we need to understand that in the context, and that can be super informative, and we'll see one way that that can be helpful here to begin with. So we're going to graph the inverse of x squared minus 2x using a table to help us. Okay, so in our table here, I've selected some values, just a few of them. This is quadratic. I should have some idea of what the function itself looks like, but let's plug some numbers in. So if I put a -1 in, I get -1 squared minus 2 times -1. So that's 1 plus 2, looks like 3 that I get out of there. If I put a 0 in, I get a 0 out. Okay? If I put a 1 in, I'm getting 1 minus 2, that's -1. If I put a 2 in, I get 2 squared, which is 4 minus 4, I get a 0 out. And if I put a 3 in, I get 9 minus 6, that's 3. Okay? So I'm going to graph the function here, first of all, in red. So this is g. G changes these x's into these y's, and I have a point at -1, 3, and 0, 0, and 1, -1, and 2, 0, and 3, 3, and I recognize the parabola happening here. I've got I could kind of sketch through here that this is what the graph of that looks like. If I want the graph of the inverse switches the roles of these things. What was the output before is now going to become the input, and what was the input is going to become the output. So I'm moving in the other direction, and I'm going to get some point, at this point 3, 3 is on the graph of the inverse as well. But then, so if I want the inverse points here, I'm going to put points at 3, 3, at 0, 2, at -1, 1, right? I'm switching the x's and the y's. So 0, 2 is right there, and negative 1 comma 1 is right there. 0, 0 is on this as well, and then 3 comma negative 1 is right there. And if I'm going to connect those dots, it's going to look something like this. So where the original parabola opened up, this one opens to the right. The vertical idea became horizontal. My vertical axis of symmetry in the original one is now a horizontal axis of symmetry in this. I could evaluate things with domain and range on this as well. Now, this particular example I did on purpose because we can get the graph of what the inverse is supposed to look like, but the inverse itself is not a function. Remember, function's got to pass that vertical line test, and the inverse here does not pass the vertical line test. Okay? So sometimes we have to look out for functions whose inverses are themselves not functions. And basically we test that on the original function with a horizontal line test. Because when we switch the horizontals and verticals and talk about inverses, then that horizontal line test will become a vertical line test, right? To see if the inverse is a function. So if a horizontal line crosses a function in more than one place, then its inverse will not be a function. Still a value sometimes to know what this thing looks like, and there are other ways to describe this in terms of reflections and things like that. But this is a quick way. If you know points that are on a function, then you also know points that are on the inverse of that function. Okay. Now, what if we want a symbolic equation? This one, 3 minus 2 over 1 minus x, does pass the horizontal line test. Its inverse is a function. And we're going to do this because it works out this way with an arrow diagram. Okay? So the first step is let's look at what f is as an arrow diagram. So there's going to be a sign change. We're going to add 1. We are going to flip that thing over, right? I'll put the intermediate steps here for the time being. Negative x plus 1 is the same thing as 1 minus x. Flip it over. I got 1 over 1 minus x, and now I need to multiply by 2 to get that 2 in the numerator. And then I will change a sign. That's a negative over 2 over 1 minus x, and I can add a 3 onto that. So it takes all of those arrows to build 3 minus 2 over 1 minus x. Okay? Get rid of the intermediate steps here. The inverse is just the kind of thing that we've done before. We want to switch the x's and y's. Before this was x, that was y. Now we're going to switch it and say, you know, this is x and this is y, and how do we get from the x to the y? Well, in the first place, we have to subtract 3. And then the opposite of sign change is a sign change, the inverse of. The inverse of multiplying by 2 is dividing by 2. The inverse of the reciprocal is the reciprocal. The inverse of adding 1 is subtracting 1. The inverse of a reflection is a reflection. And so we can start that x over here, and we'll just see what we get. So we start with the x, we subtract 3, then we change the sign. Well, sign change on that just makes it look like a 3 minus x. We're going to divide that by 2. And then the next step says flip it over. Okay, that's a 2 over 3 minus x. And then we want to subtract 1 from the whole thing and then change the sign on everything, which will change it to a positive 1 minus 2 over 3 minus x. This, we call that f, so this is f inverse of x. And the arrow diagram walks us step by step into what that inverse is going to be. All right, so as long as we know what the inverse of every arrow is, we can come up with an equation. Now, there's a couple of things like the squaring function where if we come back, it's a plus or minus square root, and that makes it look a little bit funny there, but that's what we used when we were solving quadratics. That was necessary for that. So building an inverse is very, very much related to solving an equation. Okay. All right. Sometimes you'll be asked to verify that two functions are inverses of each other. And for everything that we're going to run into in this class, if the two functions are, if one is an inverse of the other, then the other is the inverse of the one. And it will work out that way. If you go far enough in math, it's not always that way. But the way that we check, the formal way of checking that two functions are inverses of each other, is we compose them together. So f composed with f inverse of x, which should give us the same thing as f inverse composed with f of x. And if we do either of those and end up with just x at the end, which means what we started with is what we end with, then that is a verification that those things are inverses of each other. Okay? So I have a couple of functions here. G of x, which is negative 4 log base 3 of 2x minus 7, and h of x, which is 1/2 times 3 to the negative x over 4 plus 7. We want to verify that these are inverses of each other, so we are going to compose them, which means we first of all are going to make the arrow diagram for one of them. So I'll do it for G first, multiply by 2, subtract 7, do a log base 3 of, and I'm going to multiply by 4 and then change the sign. Okay. And it's composition, so the next one is getting tacked right on to the end. And the first thing that happens to that x, it looks like there is a sign change. And then a divide by 4. And then a 3 to the power. And then an add 7 and multiply by 1/2. Well, let's see what happens if we stick an x in the beginning. So the x becomes a 2x, which becomes a 2x minus 7, which becomes the log base 3 of 2x minus 7, which becomes a 4 times the log base 3 of 2x minus 7, which becomes a negative 4 log base 3 of 2x minus 7. That's not a surprise. That's what we said G was. We've just verified that G is, that we have the right set of arrows. Now it says change the sign. Well, change the sign on the sign change. That gives us a 4 times the log base 3 of 2x minus 7. Divide by 4, that's going to get rid of this 4 and get us down to a log base 3 of 2x minus 7. It says put that in the power of 3. Well, 3 to the log base 3, those are inverses of each other, so that's just going to leave me with a 2x minus 7. And 2x minus 7 plus 7 is just going to leave me with a 2x, and half of a 2x is an x, so those things are inverses of each other. Okay? And in fact, if I look up at this one where I found the inverse, this arrow diagram here is its own proof that it's the inverse. Because the blue going from left to right is f, and the green coming back is f inverse. And so it's like I could have taken that thing across the bottom and just stretched it farther to the right, and I would have ended back where I started again. That's the point of the inverse. If the function does something, the inverse needs to undo everything that the function does and get it back to where it was at the beginning. Okay? So arrow diagrams are pretty potent for doing inverses as well. And there are, as you take more math classes, they will start to do more stuff with inverses. but this is enough for us. So we'll see you in the next video.